Hi, this is part 8 of this training video series, and I will first talk about how we integrate VZMOD into ArcNLET v1 to make ArcNLET v3, and then I will give you a demo for running the full ArcNLET v3. And so you have seen this picture many times. We develop this VZMOD for simulating the video zone processes. And then we first developed ArcNLET v1 to simulate nitrate transport in groundwater only. And then we developed VZMOD for simulating the video zone processes, ammonium and nitrate transport from drain field to water table. And then we integrate VZMOD into ArcNLET to get ArcNLET v1 to get ArcNLET v3. And also we add ammonium reactive transport in groundwater. So it's not for nitrate only, it's for both groundwater and nitrate, so that we can simulate ammonium and nitrate transport from drain field to water table and from water table to a surface water body. So I'm gonna talk about the theory first and then give you a demo. So this is an overview of ArcNLET v3. So we start from the septic tank drain field and simulate absorption of ammonium and the nitrification of both absorbed and dissolved ammonium into nitrate, and then denitrification of nitrate to nitrogen gas. This is for VZMOD. And for groundwater, and those ammonium dissolved ammonium and nitrate flow into groundwater. And also we simulate absorption of ammonium and nitrification of ammonium and denitrification of nitrate, and whatever left will flow into surface water body, and that will be our load. So in the video zone process, in the video zone, the denitrification is very small because it's aerobic condition, and nitrification is dominant. In groundwater, nitrification will be minimal, and denitrification will be dominant because groundwater is more anaerobic condition. And so the simulation, this is a loosely coupled. So we got ammonium and nitrate concentration at water table by using VZMOD, and then we use the concentration at the water table as a boundary condition to ArcNLET v1. But the key point or the key challenge is to how to add reaction and transport of ammonium. So in theory, we should solve two sides of equations. One is for ammonium, the other is for nitrate, and these two equations are very similar to what you saw for VZMOD. So this is ammonium, and we consider advection and dispersion and nitrification. And for nitrate, and this is advection, dispersion, and we have extra mass due to nitrification and the loss of nitrate due to denitrification. But for VZMOD, we can solve these two sets of equation without any problem because it's a 1D simulation just between drain field and water table. But for groundwater, this is challenging because this is 2D. You see we have XY as we discussed before. We're simulating a 2D simulation, 2D transport. So if we're solving these two equations separately, it's gonna take a lot of memory and disk space, especially memory. We save everything in the memory of ArcGIS, and by the way, the ArcGIS only manage 2 GB of memory. You cannot have a large data set to take over the entire memory. You're gonna get very slow run. So we have to think about something more efficient to solve these two equations. And there was a paper published in 1999 by Sun et al., and he introduced a very smart way to do it. So essentially, you have to do a transform. So here is the transform. Don't worry about those parameters. you just look at the big idea behind it. So you have ammonium concentration, you have nitrate concentration, and all those parameters are just parameters involved in this transport process. And like say, theta is porosity, rho is density, and absorption coefficients, nitrification rate, denitrification rate, and those are given parameter to our model. And so we're gonna do this transformation, and then we're gonna have a new variable. We call it A. This is A is for nitrate, and you can have A for ammonium. So A for ammonium will be the same as the C or concentration of ammonium. So A is just, you can think it as just a symbol. It doesn't have any physical meaning, just a mathematical symbol. And then after this transformation, you can transform this equation 2 essentially to combine these two terms together into this A term. You see here, there were 1, 2, 3, 4, 5 terms or parts in this equation. After the transform, all the C concentration become A, and then the last term become 1. And the good thing is that this equation 3 has the same form of this equation 1, so that we can solve equation 4, one equation for two species, ammonium and nitrate. So this K would be different for different species. And then after we solving this one equation, which is here. So this is a governing equation. This is a governing equation, and those are initial condition, and then boundary condition. And we again use this Dominical solution we talked before. We just solve this for A, right? And then we're gonna have this A of ammonium would be this concentration of ammonium, right? And then we have this A for nitrate right here, right? And then based on the definition we had here, we got a C for ammonium, which is A of ammonium. We got A for nitrate, and then we can solve for concentration of nitrate, which is right here, right? So you got the concentration of nitrate, and this is like a one stone for two birds. You're solving one equation for A, and then you get concentration for both ammonium and nitrate after this linear this is algebra. So this is gonna save a lot of computational memory and computational time to make this model run fast. And then we talk about the denitrification. So you need to have a denitrification or mass balance essentially for both ammonium and nitrate. So we have the same idea. You have input essentially. This is for groundwater. You have input from VZMOD. You have denitrification and for nitrate. You have absorption for ammonium and the nitrification for ammonium, they're gone. And then you have the output to water body of ammonium and nitrate, right? So you just do the mass balance, and then you have this load calculation. So this is amount of nitrification, this is amount of denitrification, and this is input, and this is input. So the difference between input and the nitrification and denitrification will give us a load to surface water body. So that's essentially what we did in theory. And we did a number of tests. And so this is one test we did to compare our results using ArcNLET, which is actually updated ArcNLET with both ammonium and nitrate. And then we compare results given by a EPA report. They have the Fortran source code, and then we compare our ArcNLET results with Fortran code outputs. And so those are parameters we choose to run the model. So we make sure we compare apple to apple on these two simulation, our ArcNLET and the EPA's source code, Fortran code, using the same set of parameter. And here is our results. We published this in a paper of Zhu et al. 2016, available at the project website. So this is the simulated ammonium using ArcNLET and the EPA's analytical solution implemented in the Fortran code, essentially you can tell they're identical. So this gives us the confidence that our coding is correct, and then we can use it for real-world application, right? So essentially, by doing this transformation, we include the reactive transport of ammonium and nitrate in groundwater aquifer. So this is video zone simulation. This is the um, flow and particle tracking. This is nitrate only. This is ammonium and nitrate. So all the change we made in ArcNLET are invisible to the users, and all the users need to do is just click several button to make selections whether they want to use nitrate only or both ammonium and nitrate, right? So from now on, I will give you a software demo for the full ArcNLET, that is to simulate ammonium and nitrate reactive transport from drain fields to surface water body. So we have three cases published in Zhu et al. And we use case 2 of this publication for the demo. And the paper can be downloaded from my website if you're interested. This is a paper. And so this case 2 simulate a portion of the Eggleston Heights neighborhood located in the city of Jacksonville with 287 septic tanks. So now I'm gonna run the model together with you. Let's see here. So I will put side by side. So I will put this on one side, and then I will put ArcNLET on the other side, so you can run it side by side. So you can tell I start from scratch. So you will see mistake I make, and there may be some embarrassment moment. Maybe I forget things, but well, let's see. So first I need open or import all the data into ArcGIS. So before using ArcNLET, so I need for groundwater flow module, I need a DEM, hydraulic connectivity, porosity, and the water bodies. So I will do that. So I will have a folder. I will call it. Well, there's always this no responding moment for my ArcGIS. I hope it doesn't crash. Okay, now it comes. So I already made well, let's see. So it's Eggleston Heights 2. Okay, so this is a folder. I will make it available to you guys online. This is case 2, prepare for my postdoc, and we have input data for running ArcNLET, and she also prepared a folder for output file. So I just created a folder this morning called output data test. So let me delete it actually, then we can run it together. So let's see, where is it? Yeah, here. So let me not this one. Let's see, where did I put it? Okay, so it's here. Yeah, so I have it here, case 2, and then this folder is what I made this morning. I will just delete it so that we can start from beginning. So now I will create a folder. I will call it output data test, so that I won't mess up its original data, because I will show you there are a lot of teeny tiny details to be taken care of during a model run. So so I will input data from input data. So actually we have a number of input data, and also we have a number of data from this folder. This folder probably look familiar to you. This is for VZMOD. As I mentioned to you, VZMOD and ArcNLET share a lot of common input files. So I will do this way. I will open things from import data from the VZMOD module. Let's see what we have there. So we have let me see, maybe I can import all. So here we have hydraulic connectivity and septic tank and LiDAR DEM and topography. Let me input those four. So so these data, and those are essentially LiDAR. Oh, I need a water body, right? So this water body is not here because VZMOD doesn't need a water body, right? But it's in this input data. So water body is right here. Water body. Okay, so here. So this is a neighborhood in city of Jacksonville. Those are septic tanks. Those are zones of connectivity and porosity. So I will not spend effort to make it nice, but you can actually see the results from the video. So look at this. This is DM. Where's my DM? So LiDAR, this should be the DM. Okay, so let me move out a little bit. Yeah, okay, so maybe, okay, so here. It's on top of it. Okay, so this is, the black thing is DM, but look at this figure. This figure is looks better. So we have DM data in color, and we have a septic tank, and then we have porosity. So we here have about 3 zone of porosity on this bigger zone, and including this one, and 2 small zones. And for connectivity, we have 2 zones, and the rest of it is 7. Well, there's small zone here along this water body, has a small value 0.69 meter per day for hydraulic connectivity, and for the rest of the domain is 7.9. So this is after you process your ArcGIS file, you're gonna have something looks like this. Of course, you have your option to select colors and symbology. So you got the, I'm sorry, okay, here you got this, and then let's run ArcNLET. So we got DM, it's a LiDAR DM 10 meter, hydraulic conductivity, and porosity, and then water body, right? So here we use a smoothing factor of 60, and we have this after calibration. We're gonna talk about this calibration later on. So essentially, you smooth DM for 60 times, then you got the shape of water table, right? So you got 60, and then have this velocity magnitude. So I will save it at this folder I just created called output data test. I will call this magnitude of 60. So I always put a smoothing factor there because this is a calibrate parameter. You may run it for another smoothing factor, and then you want to compare the output for different smoothing factor, and it's better to have the smoothing factor in your file name so that you can recognize those files. And this is magnitude, and then we have direction 60. And here, this is something new. At this moment, we will need to output smooth DM because we're gonna use a smooth DM for VZMOD. So we select this option. We don't need to output hydraulic gradient. We do not use this often actually. We sometimes use it for calibration, but if you have a forward run, you don't need to run this. So we have this and we save it. We call it smooth DM 60. So we save it. So now we can run it, execute groundwater. It's still smoothing. Let's see how fast it runs. Okay, it doesn't crash, good thing. Okay, it's finished, and of course this looks pretty ugly. Smooth DM is here, director and magnitude is here. So I will not process it to make it better, but I will move on. So this is for groundwater flow input and output file, and then I move on to the particle tracking. So for the particle tracking, okay, so I will need the input file. I need to tell where septic tank is, and then water body, and then magnitude of velocity, and direction velocity, and the porosity. It's right here. Right, and this water body resolution and step size, we can just leave it as default. I explained this for ArcNLET v1, and then the only output is the particle flow pass. We call it pass 60. So and then I run it. Okay, so it just move for each particle or each septic tank. I'm sorry. And then I would just turn this off. Let's see, and turn this off, and turn this off. Okay, so those are DEM and septic tank and water body. And you see there are small things here. Let me see if I can move it. Yeah, so there are small things here. This looks pretty weird, right? So I can warn you, those small things happen pretty often, and there are techniques to handle it. But for this demo, I will not show how to handle it. I'll just say take it or just ignore it for this moment. We just run it to see how to run it. Okay, so we're done about particle tracking, and now let's move to the next. Oops. So the next step is important. So essentially, groundwater flow and particle tracking, to run this module, the procedure of running this module are exactly the same for ArcNLET v1 and v3. But in ArcNLET v3, you would need run VZMOD first, because you need to generate, you need to simulate the ammonium and nitrate transport from drain field to water body to groundwater, and then use that ammonium nitrate concentration at water table as the concentration for the source plane for groundwater modeling, right? And so theoretically speaking, you need to just click this button to launch VZMOD, but somehow I found this morning this doesn't work that well. Although I have this Windows launched, but doesn't run, and there's an error message. I have not figured out how to solve it. Again, the car need maintenance, but I figure out another way. So we can run from this VZMOD folder in the installation. I told you before, after you download ArcNLET, you install, and the software create a folder called ArcNLET, and then you copy the VZMOD folder from the download file to this folder, right? So you run it here. Okay, we got it. So let's run from here. So we're gonna run this for sand soil, and then we're gonna run for multiple septic tank, for heterogeneous hydraulic connectivity and the porosity. Oh, by the way, if you choose this and this two file window activated, but you may notice the KS and theta R, I'm sorry, and theta S, this is hydraulic connectivity and this is porosity, and those are inactivated because we're not using those values. We're using the values from those two files, right? And then we're going to calculate the depths to water table. Okay, so I will talk that later on, and then we're going to upload the file. And so first, septic tank location. Okay, so I have to get the file input located. So it's okay, and okay, it's here. VZMOD and input. Okay, so I got the septic tank, which is shapefile right here, and then I got hydraulic connectivity. I have to do it again. Nitrate, denitrification here. Input septic tank input. This is connectivity, right? So connectivity, porosity. This is I have to do it again. Porosity. I almost there. Okay, so not here. I see this septic tank, and well, essentially they're same file. I just want to be consistent. Okay, porosity. Yeah, so DEM. So here, this is for calculating the depth of water table. If you watch probably video 6 or 7, I forgot which one, but you will know what those used for, right? So DM, I got, I have to do it again. Maybe we can make it better next time, but so far we have to do this. So this is DM, right? DM. So lighter, yeah, here DM, and smooth DM, right? So this is generated by the groundwater flow module, right? You will use that one for the simulation, but to be for demo purpose, I will use what my postdoc generated, so that things are consistent. Where did I save it? What I'm looking for? Okay. Septic tank. Okay, almost there. Smooth DM. Okay, so this is smooth DM image file, right? So don't forget about this one, the distance. If you remember what the distance is, the distance. Oh, I forgot to put it here. You have to do. Let me see if I put it here. Oh, I forgot. So you have remember to get this distance. This is A and B thing, and you have to do a calibration, and then from the calibration you get. Let me see. You get. Let me see. Where is the paper? Okay, here. Yeah, right here. So yeah. So. Okay, so this is a paper we had, and so we did this calibration. And for example, this is the we have 4 observation wells, so we can have this profile based on the measured water level at the 4 wells. So I will talk about it later on, but just to show you, this is a profile of these 4 wells of the measured water table, and this is smooth DM. Just tells you that the shape looks pretty much close to each other. And this is the light blue line is for original DM. You smooth it, you got this line, and that represents the shape of water table, right? So looks pretty good. We're gonna talk about this later on. So you do calibration, and you got measured water table and smooth DM, and this slope is what you need, right? So this slope, this is the we needed this, and also this is our A value. We need a B value, and B value we said that's 18 inch. So this is the 275 meter. So this is 275 centimeter, and so we have. Let me pull it out so you know exactly what I'm talking about. This is a training video. I wanna tell you all I did. Where did I put it? Okay, here. So, not this. This one. So this is VZMOD. Theories behind VZMOD. Maybe this one. Let's see. Okay, here. Theories behind VZMOD. So here. Oh. No, not this video. So it should be 7. Okay. So sorry about that. And so I'm not a good salesman. That just tells you what I'm thinking. So this is A and B, right? So we got DM, smooth DM, and the A is from calibration. That's 2.75 meter, and this B is this, and we said this is 18 inch we're using. So you have to convert 18 inch to centimeter. So essentially you just multiply 18 by 2.5 to convert inch from centimeter. So 18, I'm doing the calculation on my phone, is about 45 inch centimeter. So A is 275 and B is 45. So the difference between A and B here is 230 centimeters. So I will use 230 centimeter right here, right? And then output folder. So I will choose, okay, the one I just created. I called it here. I called it. Where did I put it? Here. I called it output test, right? So I just use that one, and then I will start running it. So this is reading all the oh, by the way, I forgot one thing to tell you, but it doesn't matter. We can just let it run. So when you run it, there are two things. So here, it's done. We have initial concentration 60 and 10 milligram per liter. That's the concentration of ammonium nitrate from the drain field. And here we have two important parameters. That's nitrification rate. We use 2.9 here. And then we have 2.025 for denitrification rate. And those are from a publication of MicroA. And so that's pretty much it. And so this run generate a file called okay, here is the folder I created, and this VZMOD run generate a file called septic tank. So this file is, let me open it in my ArcGIS. So I will open it in my ArcGIS. So here, so septic tank. So this is septic tank file I generating using VZMOD. VZMOD. So my original septic tank file was export out to. My new septic tank file is this one. Let's look at its attribute table. So here at the last two columns, we have a concentration of nitrate and concentration of ammonium at water table. And so you see here, essentially all ammonium become nitrate, and except a few places, and I will show you. So here, if you process or plot the septic tank file, you will get a figure like, close this one. So you have get a figure like this here. Let me maximize it so you will see it. So you get a figure like this. This is a simulated ammonium nitrate concentration at the water table by VZMOD. And you can tell that the blue, this is for ammonium and this is for nitrate. For ammonium, for most places, the ammonium concentration is essentially zero because all ammonium is nitrified, right? Except near the river, because near this surface water body, the water table is shallow, so the nitrification process is not completed. So I will show you a picture later on how shallow the water table could be. So essentially there is no nitrification. All ammonium remain as ammonium and enters water table. Let's see. This is for nitrate. Nitrate concentration is high and near inland, but it's low along the water table. So this is what we do after VZMOD. And then you start running, you start running your transport. So here we're done about this. And so here we're gonna run ammonium and nitrate transport in groundwater, right? And so now I have two options of septic tank. This one is original one. This is a new one with updated concentration of ammonium nitrate. I will certainly select that, and those are black out or yellow out. I will not use C0 here. I will use C0 here. And water body, nothing changed. Flow path, nothing changed. And I will use this decay because I have denitrification. And then come here. I will specify Z in this case. So my Y is 6 meters. So I will go here and specify Z, right? So I will use 1 meter. So this is 1 meter come from calibration. I'm gonna match my data. I will explain that in another video. So for dispersion coefficient, this is also calibrated. And so we use the value of 10 for longitudinal for both nitrate and ammonium. And so here this is ammonium. We now use ammonium. And alpha Y as a transverse horizontal. We use 10. Use 1 for both ammonium nitrate. And for denitrification rate, we use a 0.008 per day, and the nitrification rate we use a 0.00025. This is also came from calibration. And the KD we use 2.0, bulk density we use 1.42. And average theta we use 0.4. So that's needed for the absorption. And then I have everything, so I will save my data. So I will save this as plume, um, say ammonium, this is nitrate, and this is for, of course, 60. And for ammonium, I have plume, uh, ammonium, and this is 60. And then I can run my transport, and so hopefully everything runs fine. Okay, it's running. Okay, good. Um, just let it run, and so it go through for this 287 septic tanks. So you first run the Dominican Robin solution, and then you need to do the post-processing, and this is the post-processing part. And then it's almost done generating output raster. And so this is again for load calculation. So you got a plume, and then you can calculate the amount of nitrification, denitrification for each cell of the each cell of the raster, and then to generate the info file, and then you're done. Okay. Um, okay. So, and yeah, you need a two step of post processing for ammonium and nitrate separately. And so yeah, I should show you. Okay, so converting to nitrate and saving files. Okay, so now you see here we have two ugly figure. So that's for plume of ammonium and a plume of nitrate. And you can play this with ArcGIS. So here what you got. And so here this is a plume of ammonium based on the ArcNLET simulation. And this is, let me maximize it. So this is a plume of nitrate. And so here we only have plume of ammonium near the water body. And those are monitoring well. We're going to use it for calibration later on. And for nitrate, there's no plume along the surface water body, but we have plume inland to the water body. And some like this doesn't have any contribution because all the ammonium or nitrate has been denitrified. So we're done about this. And the last step is the easiest part. So we can go back, and then you go to the load estimation. So this is you're going to use the info file for nitrate and info file for ammonium, and then this will take no minutes to do it. So here we have the FID of water bodies. So you can get the FID from the water body file, and then for each for each row, the first item is water body FID, and then this is the load output to the corresponding water body. And the risk factor, oh, I forgot to talk this before. So risk factor is just a engineering concept. You say, well, I want a conservative estimation. I want to multiply whatever I get by 1.5. So you put 1.5, and this column will be this column times 1.5, right? So if you say, well, I don't think I have much risk, I will use 1, so this two column will be exactly the same like here. And this column is for the amount of removal because of denitrification, and this will be the load. So if you do TMDL, this, oh, I'm sorry, this is in from the source plane. So this values are for each individual water body. If you want a total amount of load, you just add them together. And the unit is milligram per day. Keep that in mind. You need to convert milligram into pound or kilogram and whatever you want. So you're done. So then this is the whole process of using ArcNLETv3 to simulate ammonium and nitrate transport from drain field to groundwater and to surface water body, right? So in part 9, I will talk about the practice. how to prepare files and what to pay attention, what have we learned in the past, and what we would suggest to you. So we're gonna see you in part 9. So all the theoretical part is done. Starting from part 9, we're gonna talk about our practice or the real world application of ArcNLET, and then I will see you in part 9.